In this lecture, we will be looking at the topic of vector multiplication, and more specifically, the vector dot product. So first, a general question. What is vector multiplication? How do we define the product of two vectors? If we multiply two vectors, do we get a scalar? Or do we get a vector? And the answer is we get both, by defining two different types of vector multiplication. The first type, the vector dot product, results in a scalar. And the second type, the vector cross product, will be a vector. We will look at the cross product in the next lecture. In this lecture, we look at the dot product. So, how do we define the dot product? Given vectors A, A1, A2, A3, and B, B1, B2, B3, the vector dot product is the scalar, and we write it A dot B, and it's defined in the following way. You multiply the respective components of the vectors and add those products. So we multiply the first component of A with the first component of B. To that we add the product of the second component of A times the second component of B. And to that we add the third component of A times the third component of B. And you can see from the way this is defined on the right-hand side that this is a scalar. And that is very important to remember, that the dot product is a scalar result. For example, suppose we have the vectors AB given here, and we want to compute their dot product. Using our definition, we multiply the first components of each, so 1 times 2, to which we add the product of the second components, -1 times 1, to which we add the product of the third components, 2 times 3, which gives us 2 minus 1 plus 6, or 7. Some basic properties of the dot product include the following. So suppose we have vectors A, B, and C. A vector dot product with itself is the same thing as the magnitude of the vector squared. We can see that if A is, as in the previous slides, A1, A2, A3, and we take that dot with itself, we see, multiplying the first components, we get A1 squared. Multiplying the second components, we get A2 squared. And multiplying the third components, we get A3 squared. And we can see that if you were to take the square root of this, you would have the magnitude of A. And so we see that this is, in fact, the magnitude of A squared. We also have commutivity of the vector dot product. So you can do the dot product in either order, and you get the same result. And that is because of commutivity of multiplication. You can see, if we wanted to look at that second A dot B, as we saw defined in the previous slide, we can reverse the order of these products as B1A1 plus B2A2 plus B3A3, which is B dot A. And it's important to note that, because when we talk about the vector cross product in the next lecture, we will not have this property. And we see how a constant times the dot product works. You can multiply the constant times this dot product, or you can bring that constant in to multiply by either one of the vectors, and you get the same result. And we see the dot product distributes over addition of vectors in the following way. And we can prove 3 and 4 in a similar fashion to how we proved 1 and 2. The geometry of the dot product is also an interesting thing to look at. So if we think about having two vectors, say A and B, we can look at the angle between the two, theta. And we have a theorem that says if theta is the angle between two vectors, then their dot product is the length of A times the length of B times cosine of theta, which can be derived as a geometry result by looking at the triangle made between these two vectors. This is very useful, in particular for finding the angle between two vectors, because if you have the vectors A and B, you can solve for cosine theta in that equation 2. And given vectors A and B, this is something on the right that you can compute. For example, if we consider vectors V is 5i plus 5j and W equals 4j, let's find the angle between these. So we have the dot product, V dot W. 5i plus 5j means you have a 5, and a 0. And a 4j means you have a 0, 4, 0. Recalling that I is the unit vector 1, 0, 0, and j is the unit vector 0, 1, 0. Doing this dot product, we have 5 times 0 plus 5 times 4 plus 0 times 0, or 20. We can then compute the magnitudes of the two vectors. The magnitude of V, we have the sum, the square root of the sum of the squares of the entries. So for V, we have 5 squared plus 5 squared plus 0 squared, or root 50, or root 2 times 25. We can bring out the 25 as a 5 times root 2. For W, we have 3 entries, 0, 4, 0. So we have 0 squared plus 4 squared plus 0 squared, or root 4 squared, or 4. Using our formula that cosine of theta is V dot W over the product of their lengths, gives us the dot product was 20. The magnitude of V, 5 root 2, and the magnitude of W was 4. This is, of course, 1 over root 2, or root 2 over 2. And what angle, theta, has cosine root 2 over 2? And we know from our right triangle with sides 1, 1, root 2, and non-right angles 45 degrees, or pi over 4, with our SOHCAHTOA rule, that cosine of pi over 4, which is adjacent over hypotenuse, is 1 over root 2, or root 2 over 2. And so we know the acute angle between these two vectors is pi over 4. What about the special case when you have two vectors that are non-zero and their dot product is 0? So what does this mean? If you have two non-zero vectors, dot product is 0, let's think about that formula that we just looked at. So we have that cosine of theta is A dot B over the product of their lengths. We know that the denominator here is non-zero. Since both A and B are not the zero vector, they have some non-zero length. So we don't have any division by zero problem. But if A dot B is zero, then this becomes 0 over this non-zero denominator, or 0. So this means that cosine of theta is 0. And remember, theta is the angle between A and B. Well, what are the roots of cosine of theta? So let's think about the graph of cosine of theta. We know it looks like this. And what is this first root to the right of the y-axis? And we recall that that's pi over 2. So this means the acute angle between A and B is pi over 2. And recall, in degrees, that's 90 degrees. So that means A and B have this 90-degree angle. You could also think of it as being 3 pi over 2 if we were to measure the obtuse angle between the two. But what this tells us is that the dot product of two vectors being 0 tells us that the vectors are perpendicular. And this is generally how we test for orthogonality, which is orthogonal is a synonym for perpendicular. So we have that the non-zero vectors A and B are perpendicular if and only if A dot B equals 0. And this in general is the test that we will use to see if two vectors are perpendicular or orthogonal. This will come up in many different applications, in many different contexts when working with vectors. It's an extremely important property of the vector dot product. The next thing we will look at will be the vector cross product in the next lecture.